So now we're getting back into the solving quadratic equations. So far, just like a little refresher, I guess, a quadratic equation forms a parabola when you graph it. And so far, all that we've been looking at is the solutions being the x-intercepts. And that's kind of clunky because you can't get really exact answers except in very unique situations. So we need to expand off of that. You guys were doing, where is it crossing, or between what two numbers is it crossing the x-axis? So now we're going to do a different way, and it's going to be solving these quadratic equations by factoring. But we're still looking for these zeros over here. We're just not going to do it graphically. We're going to do it by factoring. And so there's some terms that you need to get straight, and you need to remember, what is a factored form? And it says right here, the factored form of a quadratic equation looks like this. And if you notice, what we have is just kind of like one big giant term where a bunch of things are multiplied together. Nothing in between them adding or subtracting. So the A would be like the greatest common factor, and this is where they did possibly the A times C method. And they give you a situation here, and you can, A is 1 times -3, factors of -3 that add to give you -2. And then they proceeded on to this, okay? One thing to keep in mind that's a little bit different is that this is an equation, so it gives us a little more latitude on things. And notice that it is set equal to 0, and that's going to be very important here in a second. These next couple terms are specifically a certain type of polynomial. The perfect square trinomial, apparently they want you to know it. I wouldn't worry overly about it, how to find it when you graph. The difference of squares is another one that if you identify it as this difference of squares, it's super easy. And then they kind of go through a couple things here of factoring. We didn't call this step using the distributive property. We called it factoring out a greatest common factor. So we did a little bit of that. And then factor trinomials. And this is just the A times C method. So now they have this idea, and they call it the key concept of the zero product property. And I think it's pretty self-explanatory, but let's take a look at it. They have so then I think where I left off here, sorry about that, is this statement right here. So we have two numbers being multiplied together, and then we're being said, well, they equal 0. And so then, I think you can think through this yourself, but obviously either A is 0 or B is 0 or both, because there's no other way you can multiply something together and get 0. And what we're going to do is use this idea in order to solve these equations. So, notice everything that they keep showing you has it set equal to 0. And that is going to be your first step in this, is to get the equation set equal to 0, or all the terms on one side. And then what we're going to do, and you can read it for yourself, is that we're going to factor it, factor that polynomial that's there, and then set all the factors equal to 0. And so this is, if you put in the time doing your factoring, this is really not going to be a big deal at all. And so I'm going to run through some of these examples, and I think I should take care of it, take care of everything for you. So, these equations can be shown up in different forms. Okay, but your number one step, and this is going to be true even when we do some of the other ways to solve these, your first step is always going to get all the terms on one side. And so, they start off here and they say, well, what happens? Well, we're subtracting the x over. So then it's going to be now -3x. And the next step is to factor out your greatest common factor, right? Once you have it set equal to 0, then you guys just fall into that list I've been telling you about to get it factored. So, just to follow along, I would just jump straight down to this step and say, well, I took a 3x out because that's what's common in 12x squared and 3x. But so the way they did it was say, okay, well, this is a 4x here. So you take a 3x out of each term individually and a 1. And then, of course, that's where the 4x minus 1 comes from. Once you have it factored, then all you have to do is set each of those factors equal to 0. And that comes from this idea up here of the zero product property. So it's a very powerful property. Because again, nothing out there can give you 0 by multiplying unless it is 0 itself. So on this first one, we're going to divide by 3 and get 0. We're going to add 1 to the other side and then divide by 4 for 1/4. And just to connect it back to the graph of a parabola, we could graph this parabola. You should notice that it opens up because a is positive, and then it's going to cross the x-axis at 0 and 1/4. All right, so we're just going to run through these examples. I do want these in your notes, but it's going to be kind of the same thing every single time. Every time you see an equation with a x squared term in it, then your first step is to get it set equal to 0. So we're going to subtract 18 over first. Negative 9 minus 18 is negative 27. And then we're going to do the a times c method, right? 1 times negative 27, and just, we were doing this a lot. So a equals 1, b equals negative 6, c equals negative 27. So it's all the same as we were doing just by factoring. So then, they're skipping a couple of the steps for you, and this is a little shortcut if you didn't pick it up yet. But factors of negative 27, that add to give you negative 6. Well, that's negative 9 and positive 3. Okay, and so they skipped some of the steps, but that's what's going on. Now, because of the zero product property, right, and they say that over here, we're going to set each of these equal to 0, and that's what this step is about. And then just solve these little equations. So we subtract 3 and add 9. So again, it's the same thing that we've been doing, just one little more step. All right, so application problem. So this is acceleration. The equation d equals vt plus 1/2 a times t squared represents the displacement d of a car. Displacement is, look at displacement as distance traveled. Of a car traveling at an initial velocity v, where the acceleration a is constant over a given time. So you just put your foot on the pedal and keep accelerating. Find how long it takes a car to accelerate from 30 to 45 miles an hour if the car moves 605 feet and accelerates slowly at a rate of 2 feet per second squared. Okay, so what is the task here? This looks like something that you guys need to be doing. But anyway, the task, right, is to find how long it takes a car to accelerate from 30 to 45 miles an hour if the car has moved this far. So our task is to find out how long it takes. Well, how will you approach this task? Well, hopefully we start plugging things in. So the key here is that we're going to find t. We're going to solve for t, and that should make sense because that's the squared variable here. And so then we got to populate this generic equation that they're telling us represents displacement with the information that we have. Where are we going to do this? Okay, so I guess I'm going to do it over here on the side. I'll do it over here so I can see it. So far we have d. We know d. D is displacement. And again, like I said earlier, that just means how far the car has traveled. So our d is going to be 605 feet. I'm going to leave out the units, but 605 feet. V is the initial velocity. I'm just going back through and rereading this, right? The initial velocity. So our initial velocity was 30. We don't know how long it took, so we're going to keep t the same. Plus 1/2 times the acceleration is here, 2 feet per second squared. So again, I'm going to leave off the units 2 feet per second squared, and that's an acceleration unit, seconds squared. Velocity, if you notice, is just miles per hour. And we might have a something going on here because we have miles per hour, and then we have feet here, so our units are kind of messed up. And this is right feet per second squared. So yeah, we got a lot of things going on. I'm going to kind of point that out here in a second. And then t squared. So the problem with what we got going on here is that we not only are we in miles and then in feet, but we're also in hours instead of seconds. So we need to really kind of change one of these into the same situation. So we're going to convert one of these, like I was saying. And since we have two values that are in feet and seconds, let's change this 30. So, this is the original equation, but we got to get our units straight. So I don't know if you've seen this before, but what we have right now is 30 miles per hour. And you write it like this so you can figure out how to convert it to feet and seconds. So this is called dimensional analysis, and maybe you saw it, and I think they do it in chemistry. Maybe you haven't seen this, but let's work on the hours first. And so the way this works is 1 hour is equivalent to 60 minutes. And see, we're multiplying all this. And then 1 minute is equivalent to 60 seconds. And so what we're going to do is, at the end of all this, I'm going to write all this out, and then we're going to multiply it all together so we can see what the conversion actually is. And so this will take care of getting our hours into seconds, and now we got to deal with the miles. And so then 1 mile, and I'm writing it this way to cancel out the units, is equivalent to 5,280 feet. And so the reason this is nice is because, what we're doing is saying, okay, so now we're going to cancel our hours, and now we're going to cancel our minutes, and that leaves us in terms of per second. And then just like that before, we're going to cancel our miles, and that will leave us in feet. So now we're in feet per second. So we're just going to multiply 30 times 5,280, and then we're going to multiply 60 and 60, and then divide those two out. And what we get is 44 feet per second. So now I'm going to rewrite this equation that we had a second ago. It's correct, but our units are all different. So now what we're going to have is 605 feet equals 44 feet per second plus 1/2 times 2 feet per second squared. And now I'm going to simplify it a little bit. So we got 605, 44t plus t squared. Okay, so now all we have to do is solve this, and again, we're going to solve it by factoring. So I'm going to subtract the 605 over, because that's always going to be your first step. And at the same time, I'm rearranging it so that it's in descending order for us. So now it's just a matter of finding, we have A being 1, we have B being 44, and C being negative 605. And so now we got to go around and, 1 times negative 605 is negative 605. And so now we got to think of factors of negative 605 that add to give us 44. So I'm going to jump off and go figure out what that is, and I'll be right back. So it actually doesn't break down too awful, but what we find, or what I found, is that 55 times 11 gives you 605. Now, of course, one of them needs to be negative. Our B value is positive, so that's going to make our 11 negative. And so, again, where we can go with this is to say that this factors into t plus 55 And I'm skipping some steps, but you can check on me, right? Because 55 times negative 11 is negative 605. 55 plus negative 11 is 44. We're going to set these equal to 0, each of them. And one of these is going to be bogus, so we're going to subtract the 55 over. Remember, what we're looking at is seconds here. We're in time. So this is totally bogus. You're not going to go back in time, so we're going to ignore that one. Add 11 to the other side. And so what we're saying is going to take, back to the original question to make sure that we're answering it. So yeah, I did some of this. What is the velocity in feet per second? So we had to deal with that. So that's going to be the 44 feet per second. So you got to mess with that. You got to be in the same units. And how long does it take the car to accelerate from there? Well, it took us 11 seconds. How do you know your solution is reasonable? Well, that goes to the fact, like, what they're asking or what they're wanting you to think about is, why is this negative 55 not make sense? Well, unless you know something I don't, we can't go back in time. Okay, so that's a good problem. I'm sure you're going to see stuff like that. So, okay, so we have check. That's for you to do. We can check that at some point, but think through that. Okay, and so you get, this should look recognizable to you. Like all of a sudden, A is not 1. So how does the process work? Well, they do like a guess and check, and I've told you about the guess and check. I wouldn't do it that way, but you're welcome to try to guess and check. But right, same kind of process. You got to get it set equal to 0 first. Okay, the way we were doing it. I'm going to write this down because, again, you can guess and check all day if you want, but right. So we say A is 3, B is 5, C is negative 2. So A times 3 is negative 6. Factors of negative 6 that add to give you positive 5. Well, that'd be 6 and negative 1. So then we were going to rewrite this. Okay, again, they skipped a little bit. We're not used to doing it this way, but that's okay. So then 3x squared plus 6x minus 1x minus 2. Right, we take a 3x out here. We're left with x plus 2. Take a negative 1 out. We got x plus 2. And then we can get to x plus 2, 3x minus 1. That's how we were doing it. They were doing guess and check. But either way, we get to the same answer there. Set both of those equal to 0. And our solutions are 1/3 and 2. Okay, so now this next section, they're talking a little bit about some of these special ones. And I wouldn't over worry about it because you actually have all the techniques that you need. The first one that they're talking about is called the difference of squares. And all they're saying here is that if you recognize that your first term is a perfect square, like x squared usually, or maybe 4x squared, or 9x squared, or 16x squared, and then your second term is also a perfect square, and there's a subtraction sign in between them, it always factors like this. So, for instance, right, we could have x squared minus 9. And that would factor into the square root of x squared is x. The square root of 9 is 3. One gets a plus and one gets a minus, and it works that way every time. Now, you can know that one, and I suggest you kind of know that because it's not too bad. Hopefully you remember these. Or you could just say, well, my A is 1, my C is negative 9. Factors of negative 9 that add together to give me 0 would be these two just the same. So, but knowing this little shortcut is helpful if you can recognize it as difference of squares. Now this other one, they're saying, oh, if you recognize it as something that's a perfect square, then perfect square trinomial, then it factors like this. But I wouldn't worry about this, like not even at all, okay? Because if you just do the A times C method, you'll just get to here, and that's about all you'll really need. Okay, now this next part, we're going to work in some of the stuff that we've been doing recently, which is complex numbers. They say not all quadratic equations have solutions that are real numbers, and this is referring to a quadratic equation that does not cross the x-axis. They are imaginary solutions. In some cases, the solutions are complex numbers in the form of a plus bi. Hopefully you remember that, where b is not 0, so that means we have an imaginary part. And so they say, for example, you know that the solution of this equation must be complex because you can't take the square root of a -4. And so this would be where you take the square root, or you can take the square root of -4, it's just not a real number. And this is where you say, okay, it has to be imaginary, so I square root of 2. Of course, I forgot my plus and minus. Sorry. Should be plus or minus. And so then we'd get x being both plus or minus 2i. And that's where they got their plus or minus 2i. Okay, so we have this factor as difference of squares. You know, the first thing I'll say is like, there's no reason to take it over here. I don't know why they would even do that. I would subtract the 81 over first. But actually, if you just see it like this, there's no reason for you to not just take a square root of both sides. So, you know, what I would do if I saw this is say, well, okay, great. So if x squared equals 81, then I'm going to take the square root of both sides, getting both a positive and a negative. And I know the square root of 81 is 9, so then I know my answer is going to be plus or minus 9. But they want to go through the difference of squares, which is wonderful. So basically they're saying, you know, the way I do it is like, okay, look, you know, this is a perfect square. I can take the square root of it. I can take the square root of that. You know, they're going through this step where they're kind of identifying it more. But I know that the square root of 81 is 9. And I know that the square root of x squared is x, right? One gets a plus, one gets a minus. And so now you set both of those equal to 0. And you get -9 and +9. So you can do it that way, but, you know, I would just do it like this over here, right? You know, you do what you want though. Okay, and so then when you do this check, you know, you can do difference of squares if that's what you're trying to go for. Okay, and now they go perfect square trinomial, but I just told you, man, I wouldn't even worry about that. So the first case is, or the first step is always going to be, right, get this thing set equal to 0. And so it's going to be a little bit more work on this one. So we subtract the 26y over, and that's going to be -48. Okay, and then on the next step, we're going to add the 13 over and get 36. And then all of this, like you can go look at you can go look at it if you want, but here's what I'm going to do. I'm going to go off to the side and do it like we've always been doing it. I don't see why that you need to know what a perfect square trinomial is. If you can factor this, then you're doing great. Okay, so the first thing I would say is, hey, look, there's a greatest common factor. It looks like it's 4 to me. And so if I take out a 4 here, then I have 4y squared minus 12y plus 9 equals 0. Now we do get a little bit more leeway when we're dealing with an equation. So it's very important to understand the difference. Since we have an equation, we're allowed to just divide by that factor that we took out. And then the 0 divided by 4 is just 0. So now we don't even need to worry about that. We don't have to carry it along like we did if we were just factoring. So we have this, a times c, we get, 4 times 9 is 36. Factors of 36 that add to give you -12, that looks like -6 and -6. You got to go find it. 4y squared minus 6y minus 6y plus 9 equals 0. Right? Out of these two, we can take out a 2y, and we're left with 2y minus 3. And we're going to take out a -3 here, and we're left with 2y minus 3. It is set equal to 0. I would pay attention to that and carry it around with you. And then we have 2y minus 3 and 2y minus 3. Notice that they're both the same. You can rewrite it as, if you want, you can rewrite it as 2y minus 3 squared, but there's really no need because we're going to set both of them equal to 0 anyway. Now we're going to solve them by adding 3 and dividing by 2. And you can do the same thing over here, but you're going to see that it comes out to be the same. So we're always looking, one thing to keep in mind, and I haven't mentioned this yet, and so then, then our answer is just 3/2 here. So I think maybe I said this once before, but the biggest exponent in your equation is how many solutions you're looking for. So we're looking for 2, and you notice that all of them have been 2 so far, except for this one. So we're looking for 2, but this one counts as twice. All right, and so then the last thing is if we have these complex solutions. And again, I wouldn't even mess with this, honestly. I wouldn't set this equally, since it ends up being kind of like difference of squares. But I mean, right here, just take the square root, but there is, for some reason, they being people in math right now, really like this factoring thing. So we're going to play along. And so all they're saying is, I don't even know how wonderful this is to look at. So they say, well, this is really minus and negative because they're forcing it into difference of squares here. And that's what they're saying over here, is that we're forcing it into be difference of squares. Super cool. But right, and this the idea here is that, well, the square root of 144 is 12. And then if we work this I in, we can actually square it and get negative 144. But I guess I would just jump, if you want to do it this way, I would just jump down to this situation. And again, they want you to do this, so I guess it is worth kind of watching here. But they treat it just like it's a difference of squares. They're actually just basically saying that it's x squared minus 144. But notice that it's not really, it's plus. But they treat it the same way, right? The square root of x squared is x. And the square, so you get an x there and an x there. The square root of 144 is a 12. We get a plus, we get a minus, but since it wasn't difference of squares, we work in our i's right there. And so then it finally gets down to, right, these two equations. You still set the factors equal to 0. So then negative 12i and positive 12i. So you should be able to do all of the book work at this point. Make sure you ask questions if you get them.